Ireda's journey in the production of vanadium alloyed cylinder bodies marks a pivotal achievement in industrial manufacturing. In 2018, the company acquired the world's largest ring rolling and cylinder rolling machine, capable of handling dimensions up to 16 meters in diameter and 3 meters in height. Manufactured by SMS Group in Germany, this state of the art equipment was instrumental in pushing the boundaries of cylinder production, particularly for high stakes applications in nuclear power and deep sea engineering. The advanced machinery integrates precision control systems and innovative forging technologies to achieve superior material properties and dimensional accuracy. These capabilities are critical for producing components that can withstand extreme operating conditions, such as high pressure, radiation, or corrosive environments. Vanadium alloyed steels are particularly chosen for their unique combination of strength, toughness, and resistance to heat and wear. Vanadium acts as a microalloying element, refining grain size and improving the steel's overall mechanical performance. This makes it ideal for pressure vessel applications, this including hydrogen reactors and high-temperature gas-cooled reactors, where safety and durability are paramount. The alloying process involves careful compositional control to ensure the steel achieves optimal properties. Vanadium's ability to form stable carbides and nitrides enhances creep resistance and prolongs the service life of the material under high stress and elevated temperatures. Innovations in cylinder production. Ireda's expertise extends beyond equipment to encompass process innovations. Recently, the company achieved a significant technological breakthrough in manufacturing large diameter, thick walled, forged, and rolled sections for hydrogen reactors. This advancement addresses the growing demand for hydrogen infrastructure, as hydrogen is increasingly viewed as a cornerstone for clean energy transitions. The cylinders produced for hydrogen reactors must meet stringent standards for hydrogen embrittlement resistance and fatigue strength. Ireda's process involves multi-stage forging, precise heat treatment, and stringent quality control protocols to ensure the final products meet or exceed international standards such as SME and ISO certifications. In the field of nuclear power, particularly high-temperature gas-cooled reactors, HTGRs, IREDA has made continuous strides. HTGR cylinders are subjected to extreme thermal gradients and radiation exposure, necessitating robust materials and flawless manufacturing. IREDA's vanadium alloyed cylinders are designed to endure these challenges, ensuring long-term operational stability and safety. The production process for these cylinders integrates advanced simulation techniques, including finite element analysis to predict and optimize the material's behavior during forming and in-service conditions. This minimizes the risk of defects and maximizes performance reliability. Manufacturing process overview. 1. Raw material selection. High purity steel ingots with vanadium and other alloying elements are chosen for their tailored properties. 2. Heating and forging. The ingots are heated in precision-controlled furnaces before undergoing forging to achieve the desired preliminary shape and grain refinement. 3. Ring rolling and cylinder rolling. The heated blanks are processed using the 16-meter diameter rolling machine to form seamless cylinders with exceptional dimensional tolerances. 4. Heat treatment. Cylinders are subjected to multiple heat treatment cycles, including quenching and tempering, to enhance toughness and uniformity. 5. Non-destructive testing (NDT). Advanced NDT methods, such as ultrasonic and radiographic inspections, ensure the absence of internal defects. 6. Machining and finishing. The cylinders are precisely machined to meet exact specifications before undergoing surface treatments to enhance corrosion resistance. 7. Final quality control. The final products are rigorously tested for mechanical properties, dimensional accuracy, and chemical composition compliance. Areda's vision and expertise. With a strong foundation in technical research and extensive manufacturing experience, Areda remains a leader in producing high-performance cylinders for a wide range of critical applications. Their advancements not only bolster industries such as nuclear power, hydrogen energy, and deep-sea exploration, but also pave the way for innovative solutions in future engineering challenges. Areda's commitment to technological excellence ensures that they are well equipped to meet evolving industry needs, providing tailored solutions to address complex requirements for advanced cylinder systems. Steel balls used in crushers are critical components designed to endure extreme conditions of high stress, impact, and abrasion. Their production involves meticulous processes that enhance their durability, strength, and impact resistance. These balls find extensive applications in the mining, cement, and aggregate industries, where they play a vital role in grinding and crushing operations. Material selection. High carbon steel or alloy steel is the primary material for manufacturing steel balls due to their inherent hardness, wear resistance, and ability to withstand mechanical stresses. Additional alloying elements like chromium, manganese, or molybdenum may be introduced to enhance specific properties. Chromium improves corrosion resistance and hardenability. Manganese increases tensile strength and wear resistance. Molybdenum enhances toughness and high temperature strength. Before manufacturing begins, the raw materials undergo rigorous chemical and mechanical testing to verify composition, purity, and other critical parameters. Spectroscopy, tensile testing, and metallographic analysis are commonly employed techniques. Cutting. Steel rods or billets are precision cut into small cylindrical pieces, slugs, of uniform size. Automated cutting ensures consistency and minimizes material wastage. Forging. The slugs are heated in a furnace to temperatures ranging between 900 to 1200 degrees Celsius to achieve malleability. This high temperature also activates recrystallization processes, which refine the grain structure, enhancing mechanical properties. Drop forging. In traditional methods, a drop forge hammer or hydraulic press shapes the heated slugs into near spherical forms. For modern processes, automated forging systems allow for better control over the shaping process, ensuring uniformity and reducing material defects. Continuous rolling. An alternative process involves continuous rolling machines that pass the steel through rolling dies, forming spherical shapes efficiently. Continuous rolling is preferred for high-volume production due to its speed and precision. Excess material, known as flash, formed during forging is trimmed to create near-perfect spheres. This process is usually carried out by automated flash removal machines, which also smoothen rough edges. The steel balls are reheated in a controlled atmosphere furnace to a critical temperature, austenitizing. They are then rapidly quenched in oil or water, a process that induces martensitic transformation, resulting in high hardness and wear resistance. To balance hardness with toughness, the balls are reheated to a lower temperature, typically 150 to 650 degrees, and allowed to cool slowly. This process alleviates internal stresses, reduces brittleness, and ensures the balls can withstand impact loads without fracturing. Specialized grinding machines achieve precise dimensions and a smoother surface finish. This step ensures uniformity in size and shape, critical for maintaining operational efficiency in crushers. The balls are passed through sieves or advanced optical systems to ensure diameter uniformity. High-precision instruments like micrometers and calipers verify adherence to tight tolerances. Finished steel balls are subjected to rigorous quality checks, including dimensional inspection, ensures consistency in size and roundness. Hardness testing. Rockwell or Brinell hardness tests confirm compliance with specified standards. Simulated load testing evaluates the performance of the balls under conditions mimicking real-world crusher loads. Performance characteristics of finished steel balls. The final products exhibit uniform diameter, critical for even load distribution in crushers. High hardness ensures resistance to wear and deformation. Excellent impact resistance allows the balls to absorb and dissipate energy during crushing. Long service life reduces operational costs in heavy-duty applications. The steel balls are engineered to endure the extreme stresses and abrasive environments in crushers, making them indispensable in industries like mining, cement production, and aggregate processing. Sustainability considerations. Manufacturers are increasingly adopting energy-efficient furnaces, advanced forging methods, and waste recycling to minimize environmental impact. Efforts to use cleaner alloying elements and optimize production processes are ongoing, aiming to align with global sustainability goals.
Large or gigantic. The wording quickly makes frequent use of superlatives when it comes to describing the world's largest and most powerful hydraulic closed-die forging press. Today's machines are becoming bigger. Their components are becoming larger, their geometries are becoming more complex and sophisticated, and demand a higher press force for their production. A gigantic hydraulic forging press is a marvel of modern engineering. These behemoths are capable of exerting tremendous forces, on the order of millions of tons, to shape massive pieces of metal. The largest hydraulic forging press in the world is located in China and has a capacity of 80,000 tons. That's the equivalent of the weight of 160 Statues of Liberty. Hydraulic forging presses are used to create a wide variety of products, including aircraft landing gear components, turbine blades, and oil well equipment. The forging process itself is quite simple. A hot piece of metal is placed between two dies, and then the press ram applies pressure to force the metal into the shape of the dies. The use of hydraulic forging presses has several advantages over other metalworking techniques. For example, hydraulic forging can produce parts with a very fine-grained structure, which makes them strong and resistant to fatigue. Additionally, hydraulic forging can be used to create parts with very complex shapes. The forging hydraulic press is a massive machine used to exert incredible pressure to shape large pieces of metal. The base of the press, a giant steel structure that houses the other components and absorbs the forces generated during forging. A large cylinder containing a piston that expands and contracts using hydraulic fluid to create the pressing force. Large, flat plates that sandwich the metalwork piece between them. The movable platen is connected to the piston and applies pressure to the workpiece when the piston extends. A system that generates high-pressure hydraulic fluid to drive the piston in the cylinder. A computer or hydraulic control system that regulates the pressure, speed, and position of the moving platen during the forging process. Frame construction. The frame is welded from large sections of steel and reinforced to withstand the immense forces involved. Hydraulic cylinder. The cylinder is machined from high-strength steel and honed to create a smooth surface for the piston. Seals are installed to prevent hydraulic fluid leaks. Platen assembly. The platens are machined from steel plates and treated for wear resistance. Guideways may be incorporated to ensure proper alignment during movement. Hydraulic power unit. High-pressure pumps, valves, piping, and a reservoir are assembled to create a system capable of generating the required hydraulic pressure. Assembly and installation. The individual components are assembled and mounted within the frame. Pipelines are connected to route hydraulic fluid. Control system integration. Sensors and control valves are integrated with a computer system to regulate the press operation. Safety features are incorporated. Testing and commissioning. The press undergoes rigorous testing to ensure it meets performance and safety standards. To be able to forge such a large object, only these giant machines can meet the requirements. It is not only strong but also skillful to be able to forge steel structures according to requirements. Always need high precision in each step, because these details are not cheap. If just one of the important steps is wrong, these giant lumps of steel may have to be taken to the scrapyard for recycling. The open die forging press impresses with its huge pressing force and overturning force, with high travel speed and forging speed, as well as flexibility and high productivity. A billet weighing about 30 tons and with a temperature of 1250 degrees Celsius is taken from the furnace. It is transported by crane to the forging press. The manipulator takes over the ingot and places it into the press. The forging press is prestressed with tie rods, giving it its high rigidity and precision guidance. The operator controls the forging process on this workpiece. The HUD section of the ingot is stretch forged as a gripping neck. The workpiece is then reheated. In the meantime, the press is fitted with an upsetting plate with a hole for the gripping neck. The upper offsetting plate is positioned by the manipulator. The workpiece is positioned again. The ingot is now upset. The clamping and tensioning neck controls are forged under program control, so the material receives a uniform high-quality microstructure throughout the core. The workpiece is first forged into a square shape, then into shape octagonal. The finished forging is shipped away for quick refitting. The forging plant has, among other things, a sliding die for 3 dies, a table shifting device, and an upper clamping and rotating device for quick tool changes. A polygonal billet weighing about 70 tons is formed here again, formed by tension forging of the clamp neck. In 1794, Welsh iron master Philip Vaughan patented a design for ball bearings to support the axle of a carriage. Development continued in the 19th and early 20th centuries, spurred by the advancement of the bicycle and the automobile. There are thousands of sizes, shapes, and kinds of rolling bearings. Ball bearings, roller bearings, needle bearings, and tapered roller bearings are the major kinds. Sizes run from small enough to run miniature motors to huge bearings used to support rotating parts in hydroelectric power plants. These large bearings can be 10 feet, 3.04 meters, in diameter and require a crane to install. The most common sizes can easily be held in one hand and are used in things like electric motors. In these bearings, the rolling part is a ball, which rolls between inner and outer rings called races. The balls are held by a cage, which keeps them evenly spaced around the races. In addition to these parts, there are a lot of optional parts for special bearings, like seals to keep oil or grease in and dirt out, or screws to hold a bearing in place. We won't worry here about these fancy extras. Almost all parts of all ball bearings are made of steel. Since the bearing has to stand up to a lot of stress, it needs to be made of very strong steel. The standard industry classification for the steel in these bearings is 52,100, which means that it has 1% chromium and 1% carbon, called alloys when added to the basic steel. This steel can be made very hard and tough by heat treating. Where rusting might be a problem, bearings are made from 440 coulomb stainless steel. The cage for the balls is traditionally made of thin steel, but some bearings now use molded plastic cages because they cost less to make and cause less friction. The basic material requirements of precision roller bearings largely depend on the working performance of bearings. The selection of materials for rolling bearings has a great influence on their performance and service life. In general, the main forms of the damage of rolling bearings are fatigue spalling under the action of alternating stress, and the loss of bearing accuracy due to friction wear. The manufacturing process for giant roller bearings is complex and requires specialized equipment and expertise. The bearings are typically made from high-grade steel that is forged and machined to meet precise specifications. The rollers and races of the bearings are often heat-treated to improve their strength and durability. Because of their size and complexity, giant roller bearings can be quite expensive. However, their durability and reliability make them a cost-effective solution for many heavy-duty applications. Tapered roller bearings are commonly used in drivetrains or wheel bearing arrangements of commercial vehicles. In the German automotive industry, more than 10 million tapered roller bearings are used annually. They can support comparably high loads due to the linear contact between tapered rollers and raceway. Due to their contact angle, these loads can act in radial, axial, and combined directions. In addition, they can support high tilting moments in small installation spaces without the need for support of additional bearings. Tapered roller bearings usually operate under both grease and oil lubrication. Radial tapered roller bearings consist of an inner and outer ring between which the conical rolling elements are located. The conical rolling elements are guided along the inner ring rib. In loaded tapered roller bearings, considerable frictional dissipation occurs between the rib and the roller ends, particularly at low rolling speeds. Start-up and maneuvering are common cases in which low rolling speeds occur in wheel bearings of a truck. This can lead to a risk of wear and, in severe cases, failure. The increased frictional dissipation occurs due to insufficient lubricant film thicknesses in the roller and rib contact. The rough-cut races are put into a heat-treating furnace at about 1,550 degrees Fahrenheit, 843 degrees Celsius, for up to several hours, depending on the size of the parts. Then dipped into an oil bath to cool them and make them very hard. This hardening also makes them brittle, so the next step is to temper them. This is done by heating them in a second oven to about 300 degrees Fahrenheit, 148.8 degrees Celsius, and then letting them cool in air. This whole heat treatment process makes parts which are both hard and tough. The inner and outer ring raceways are segments of cones, and the rollers are tapered so that the conical surfaces of the raceways and the roller axis, if projected, would all meet at a common point on the main axis of the bearing. This geometry makes the motion of the cones remain coaxial, with no sliding motion between the raceways and the outside diameter of the rollers. This conical geometry creates a linear contact patch, which permits greater loads to be carried than with spherical ball bearings, which have point contact. The geometry means that the tangential speeds of the surfaces of each of the rollers are the same as their raceways along the whole length of the contact patch, and no differential scribbing occurs. The rollers are stabilized and restrained by a flange on the inner ring, against which their large end slides, which stops the rollers from popping out due to the pumpkin seat effect of their conical shape. The larger the half angles of these cones, the larger the axial force that the bearing can sustain.
老板。直接看那个后头。
这个吗？这个是冲压模式器。先做了，直接就说冲上去。
3老板，4老板。
要求看一条路。